If every new feature makes your model noisier instead of smarter, it is not just the data, it is the regularization. We will compare L1 and L2 in Python, so you can see how each penalty changes the weights and generalization. You have a model that learns training noise and then surprises you on new data. You want to tame complexity without throwing away useful signals. By the end of this video, you will see how two simple penalties change the learned weights and which one helps in sparse versus dense settings. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. Regularization is a tool you reach for when models fit too tightly to training examples. In practice, this happens in regression, when many correlated features push coefficients to extreme values, and in classification, when complex decision surfaces memorize noise. Success looks like lower error on unseen data and more stable, interpretable coefficients. Regularization is lightweight to add and often gives big improvements on modest datasets. At a high level, L2 penalizes large coefficients by pushing them towards zero smoothly. L1 pushes many coefficients exactly to zero, giving sparse models an implicit feature selection. Think of L2 as gentle shrinkage and L1 as selective pruning. If you want stable predictions when most features matter a little, L2 is a good default. If you suspect only a few features matter, L1 can discover them and simplify the model. We will build a small regression example and compare an unregularized baseline, Ridge for L2 and Lasso for L1. Then pick the best penalty on a holdout set so you see the whole workflow. Now we will fit the baseline model. This snippet fits an unregularized linear model and reports baseline RMSE. This snippet loads the toy dataset, splits it into training and test, and fits a plain linear regression as a reference point. The core idea is to measure how well ordinary least squares predicts without any penalty. The key lines create the features matrix and target vector, run the train test split, instantiate the linear regression model, and call fit on the training split. Finally, the snippet predicts on test and computes the root mean squared error, using the mean squared error metric and a square root to get RMSE. That baseline number shows how much room regularization has to improve generalization. Next, we will add L2 regularization. This snippet applies L2 ridge regularization and measures coefficient shrinkage. This snippet swaps the unregularized solver for ridge and fits on the same training split, so results are comparable. The main idea is that ridge adds a penalty proportional to the square of coefficient magnitudes, which discourages any single weight from growing too large. In the code, the critical parameter is alpha, which controls penalty strength. A larger alpha shrinks coefficients more and can reduce variance but increase bias. After fitting, the snippet prints the new RMSE and also inspects the model coefficients to show they are smaller in magnitude compared with the baseline, illustrating the smoothing effect of L2. Next, we will compare fits directly. This snippet compares OLS and ridge to see which fits training data. This snippet computes both training and test errors for the unregularized model and the ridge model so you can see the overfitting gap. The concept is simple. A model that fits training much better than test is overfitting, and ridge should reduce that gap by shrinking coefficients. The key actions are fitting both models, predicting on the training set and the test set, and reporting both RMSE values. Watching the pair of numbers shows whether ridge is actually lowering test error at the cost of rising training error, which is the expected trade-off when taming complexity. Next, we will try L1 sparsity. This snippet uses L1 lasso to zero out unneeded features. This snippet swaps ridge for lasso to show how an absolute value penalty encourages exact zeros in coefficients. The main idea is that lasso can perform variable selection by pushing small weights to zero, which helps when only a few features matter. In the code, the adjustable parameter is again alpha, controlling how aggressively coefficients are set to 0. Increasing alpha produces more zeros and a simpler model. After fitting the snippet prints which coefficients are 0 and the resulting RMSE on the test split, letting you see a sparse model that may be easier to interpret and deploy. Next, we will pick the best penalty using a holdout. This snippet picks the better penalty using a small holdout set. This snippet creates a validation loop that evaluates several alpha values for Ridge and Lasso on a holdout set and selects the model with the lowest validation RMSE. The logic is to avoid cheating by tuning on the test split. Instead, we use a small holdout to compare penalties and then report the chosen model and its test performance. The core steps are training models across a grid of alphas, predicting on the holdout, tracking RMSE, and selecting the best configuration. That chosen model gives a simple, repeatable way to pick the right regularization strength for your data. Recap: L2 Ridge shrinks coefficients smoothly and often improves stability when many features contribute. L1 Lasso drives coefficients to exact 0 and finds a compact, interpretable subset. Use L2 when features are dense and correlated. Use L1 when you expect sparsity. And watch out because L1 can be unstable when features are highly correlated. Next step: tune the alpha parameter with cross-validation across a finer grid for both Ridge and Lasso and compare their cross-validated RMSE to choose the practical winner for your dataset. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.